Hello there, and welcome to this quiet space where time moves slowly and the past is allowed to unfold without hurry. Tonight we're going to step back, not just years or centuries, but tens of thousands of years, to a moment when the Earth itself convulsed and humanity faced a test unlike any before or since. This is the story of the Toba supervolcano, a geological giant that erupted approximately 74,000 years ago in what is now northern Sumatra. The explosion was so vast that it remains the largest volcanic event of the last 2 million years. For years afterward, darkness spread across the planet. Temperatures dropped, photosynthesis faltered, and somewhere in that dimness, small groups of early humans persisted, relying on ingenuity, cooperation, and the shelter of specific landscapes. If you've heard the claim that this eruption nearly ended humanity, reducing our ancestors to just a few thousand survivors, you've encountered one of the most dramatic hypotheses in paleoanthropology. The truth, as we'll see, is more nuanced. The eruption was immense. The consequences were severe in many regions. But the story of survival is not one of simple catastrophe. It's a story of refugia, of coastal sanctuaries and river valleys, of social networks that stretched across territories, and of behavioral flexibility that set our species apart. Before we begin, I'd like to know where in the world you're listening from tonight, and what time it is where you are. Funny, isn't it? We're about to talk about an event that happened 74,000 years ago, and yet here we are, separated by miles and time zones, sharing this same quiet moment. No matter where or when you are, I'm glad you're here. If this kind of slow, reflective exploration is your kind of story, I'd be grateful if you tapped like or subscribed. It helps this quiet signal reach other curious minds. No pressure, of course, just an invitation, so settle in, maybe lie back if you can. Let your thoughts slow to the pace of geological time. We're going to walk through the evidence piece by piece and see what 74,000 years of ash, ice and bone can tell us about resilience. If you were to travel to northern Sumatra today, you would find yourself standing at the edge of a vast body of water. Lake Toba stretches across the landscape, its surface calm, reflecting the sky. The lake is enormous, holding over 240 cubic kilometers of fresh water. It is the largest volcanic lake on Earth. But this is not a lake formed by rivers or glaciers. Lake Toba fills a caldera, a depression left behind when the ground collapsed after a catastrophic eruption. The caldera itself is oval, measuring approximately 35 kilometers in one direction and 100 kilometers in the other. Within the lake, an island rises from the water. Samosa Island is not a typical island. It is what geologists call a resurgent dome, a section of the lake floor that has been pushed upward by residual pressure from the magma chamber below. Samosa is the largest and most actively deforming resurgent dome of any known caldera on the planet. The size of the caldera tells us something about the scale of what happened here. When a volcanic eruption empties a magma chamber, the overlying rock loses support. The land collapses inward, forming a depression. The larger the eruption, the larger the collapse. The Toba caldera is immense because the eruption that created it was immense. This is not the only eruption that Toba has produced. The volcano has been active for over 1 million years, with several major eruptions in its history. But the most recent event, the one that formed the current caldera, was the most powerful. It occurred approximately 74,000 years ago during a period known as the Late Pleistocene. This eruption is referred to as the youngest Toba eruption, and it is classified as a VEI8 event. The Volcanic Explosivity Index, or VEI, is a scale used to measure the magnitude of volcanic eruptions. It ranges from 0 to 8. A VEI8 eruption is the highest category, representing an explosion that ejects more than 1,000 cubic kilometers of material. To understand what that means in practical terms, consider the eruption of Mount Tambora in 1815. Tambora is famous for causing the year without a summer in 1816, a period of global cooling that led to widespread crop failures and famine. Tambora was a VEI7 eruption. The Toba eruption was an order of magnitude larger. Scientists estimate that Toba ejected between 2,800 and 5,300 cubic kilometers of material, measured as dense rock equivalent. This volume is difficult to visualize. If you were to spread that material evenly across the entire United States, it would form a layer several meters thick. The immediate geological consequence of the eruption was the formation of the caldera. The magma chamber beneath Toba had been accumulating volatile rich magma for a long period, possibly tens of thousands of years. The chamber was enormous, with estimates suggesting a volume of around 50,000 cubic kilometers. When the eruption began, the pressure was released catastrophically. The chamber emptied rapidly, and the overlying crust collapsed into the void. Today, the lake that fills this depression is tranquil. Rainwater has accumulated over thousands of years, creating a freshwater reservoir. The surface is still, but beneath that stillness, the geological processes continue. The magma chamber, though vastly reduced, has not disappeared. It continues to generate heat and pressure, slowly pushing the lake floor upward. Samosir Island is the visible evidence of this ongoing deformation. The island rises from the water, a reminder that the forces which created the caldera have not entirely subsided. The landscape around Lake Toba is lush and green. Vegetation covers the hills. Communities have settled along the shores. The land appears stable, peaceful. But the caldera remains one of the most geologically significant features on Earth, a scar left by an eruption that altered the planet's atmosphere and potentially the trajectory of human history. To understand why the Toba eruption was so powerful, we need to look at the geological setting. Toba sits at the junction of major tectonic fault lines in one of the most seismically active zones on the planet. This is not an accident. The location of the volcano is directly tied to the processes occurring deep beneath the Earth's surface. The island of Sumatra lies along the boundary between two tectonic plates. To the west, the oceanic crust of the Indo-Australian plate is moving toward the Eurasian plate. Where these two plates meet, the denser oceanic crust is forced downward, sliding beneath the lighter continental crust of Sumatra. This process is called subduction. As the oceanic plate descends, it carries with it water and other volatile compounds trapped in the rock. The increasing pressure and temperature at depth cause these volatiles to be released. The released water lowers the melting point of the surrounding mantle rock, generating magma. This magma is less dense than the surrounding rock, so it begins to rise. Over time, it accumulates in chambers beneath the surface. The magma is rich in volatiles, particularly water vapor and gases like sulfur dioxide and carbon dioxide. These dissolved gases are what give explosive eruptions their power. As magma rises and pressure decreases, the gases begin to separate from the liquid rock, forming bubbles. When the magma reaches the surface, the sudden release of pressure causes these gases to expand violently, fragmenting the magma into ash and driving the explosive eruption. At Toba, the geological setting was particularly conducive to the accumulation of large volumes of volatile rich magma. The subduction zone off the coast of Sumatra is fed by the Investigator Fracture Zone, a region of the oceanic crust that is especially fluid-rich. As this material subducted, it delivered an unusually high volume of water and volatiles to the mantle below Sumatra. Over tens of thousands of years, possibly longer, magma accumulated at the base of the continental crust. The chamber grew, fed by the continuous supply of rising magma. The size of the magma chamber is critical. Larger chambers can produce larger eruptions. Estimates suggest that the Toba magma chamber held around 50,000 cubic kilometers of magma before the youngest Toba eruption. This is an extraordinary volume. For comparison, the magma chamber beneath Yellowstone, one of the largest active volcanic systems in the world, is estimated to contain around 15,000 cubic kilometers of magma. Toba's chamber was more than 3 times larger. The magma did not erupt continuously. Instead, it built up over time, accumulating pressure. The overlying rock acted as a cap containing the magma. But rock has a breaking point. Eventually, the pressure within the chamber exceeded the strength of the rock above. When the cap failed, the eruption began. The failure likely started with a fracture, a crack in the overlying rock. Once the fracture opened, the pressure drop was instantaneous. The dissolved gases in the magma expanded rapidly, driving the magma upward through the fracture. The expansion generated more fractures, accelerating the process. Within a short time, the entire system was breaching. Magma, ash, and gas exploded from the surface. The eruption was not a single event, but a series of pulses. Each pulse ejected enormous volumes of material. The magma chamber emptied rapidly, and as it did, the overlying rock lost support. The surface began to collapse, forming the caldera. The collapse itself may have triggered further eruptions, as the shifting crust opened new pathways for magma to reach the surface. The result was the ejection of thousands of cubic kilometers of material. Some of this material fell back to Earth close to the source, forming thick deposits of ash and pumice, but much of it was carried high into the atmosphere, where it would have a far more profound and lasting impact. The geological architecture of Toba, the subduction zone, the volatile rich magma, the enormous chamber, created the conditions for a super-eruption. The eruption was not a random event, but the inevitable result of processes operating over geological timescales. The magma had been accumulating for tens of thousands of years. When it finally erupted, it did so with a violence that reshaped the landscape and sent shockwaves through the planet's climate system. 74,000 years ago, during the late Pleistocene, the Toba supervolcano erupted. The late Pleistocene was a time of significant climate variability. Ice sheets advanced and retreated across the northern continents. Sea levels rose and fell. Global temperatures fluctuated. Against this backdrop of natural variability, the Toba eruption was an abrupt and violent intrusion. The eruption is classified as a VEI-8 event, the highest category on the Volcanic Explosivity Index. This classification is based on the volume of material ejected and the height of the eruption column. For a VEI-8 eruption, the volume exceeds 1,000 cubic kilometers, and the eruption column can reach altitudes of more than 25 kilometers. The Toba eruption met and exceeded these criteria. The volume of material ejected is estimated at between 2,800 and 5,300 cubic kilometers, measured as dense rock equivalent. This measurement accounts for the fact that much of the ejected material was fragmented and expanded during the eruption. The dense rock equivalent gives a sense of the actual volume of magma involved. Even at the lower end of the estimate, the eruption was colossal. To provide a point of comparison, consider the 1815 eruption of Mount Tambora in Indonesia. Tambora ejected approximately 160 cubic kilometers of material, making it a VEI-7 eruption. The eruption caused the year without a summer in 1816, a period of abnormal cold that resulted in widespread crop failures and famine across Europe, North America, and Asia. The Toba eruption was an order of magnitude larger. If Tambora could disrupt the global climate for a year, the potential impact of Toba was correspondingly greater. The eruption ejected a mixture of ash, pumice, and volcanic gases. Ash consists of tiny fragments of rock and glass, formed when magma is shattered by the explosive expansion of gases. Pumice is a frothy volcanic rock, full of gas bubbles, light enough to float on water. Both materials are carried high into the atmosphere by the force of the eruption. The volcanic gases, primarily water vapor, sulfur dioxide, and carbon dioxide, are also injected into the atmosphere. These gases play a critical role in the climate effects of volcanic eruptions. The material ejected by Toba is known as the youngest Toba tuff, often abbreviated as YTT. Tuff is a type of rock formed from volcanic ash that has been compacted and cemented over time. The youngest Toba tuff is found in thick deposits around the volcano and in thin layers thousands of kilometers away. The distribution of this material provides evidence for the eruption's scale and reach. Close to the source, the devastation would have been immediate and total. The eruption column would have towered above the landscape, a roiling cloud of ash, gas, and rock fragments. Pyroclastic flows, fast-moving currents of hot gas and volcanic matter would have swept across the surrounding terrain, incinerating everything in their path. The flows can travel at speeds exceeding 100 kilometers per hour and reach temperatures of several hundred degrees Celsius. Nothing within tens of kilometers of the eruption would have survived. As the eruption continued, the ash column climbed higher. The force of the eruption, driven by the explosive expansion of volcanic gases, propelled the material upward. The column reached altitudes that breached the troposphere, the lowest layer of the atmosphere, and entered the stratosphere. The stratosphere begins at an altitude of approximately 10 to 15 kilometers, depending on latitude, and extends to about 50 kilometers. Once in the stratosphere, the volcanic material encountered different atmospheric conditions. The stratosphere lacks the vertical mixing and precipitation that characterize the troposphere. Material injected into the stratosphere can remain aloft for years, spreading globally through high-altitude winds. The Toba eruption column is estimated to have reached altitudes exceeding 45 kilometers. This estimate is based on analysis of sulfate peaks found in Antarctic ice cores. These peaks, which record the deposition of volcanic sulfate on the ice sheet, show a specific chemical signature known as sulfur mass-independent fractionation. This signature is produced only when sulfur compounds are exposed to intense ultraviolet radiation, which occurs at very high altitudes. The presence of this signature in the ice core record confirms that the Toba eruption injected material deep into the stratosphere. The immediate geological aftermath was the formation of the caldera. As the magma chamber emptied, the overlying crust lost support and collapsed inward. The collapse formed an oval depression, approximately 35 by 100 kilometers. Over time, rainwater filled the depression, creating Lake Toba. The lake now holds over 240 cubic kilometers of fresh water, making it the largest volcanic lake in the world. But the true impact of the eruption was not local. The material injected into the stratosphere would spread across the planet, carried by high-altitude winds. The ash and gases would remain aloft for years, altering the Earth's climate in ways that would have profound consequences for life on the surface below. The height of an eruption column determines how far and how long volcanic material will remain in the atmosphere. For small eruptions, the column may reach only a few kilometers, and the ash falls back to Earth within hours or days. For larger eruptions, the column can breach the troposphere and enter the stratosphere. Once in the stratosphere, the material can remain aloft for years and spread globally. The Toba eruption column reached extraordinary heights. Analysis of Antarctic ice cores provides evidence for this. Ice cores are cylinders of ice drilled from ice sheets, preserving a record of past atmospheric conditions. Each layer of ice corresponds to a specific year, and the ice traps particles and gases from the atmosphere. By analyzing the composition of these layers, scientists can reconstruct past events. In the Antarctic ice cores, there is a distinct layer that dates to approximately 74,000 years ago. This layer contains elevated levels of sulfate, a compound formed when sulfur dioxide from volcanic eruptions reacts with water vapor in the atmosphere. The sulfate in this layer has a specific chemical signature known as sulfur mass-independent fractionation, or SMIF. This signature is produced when sulfur compounds are exposed to intense ultraviolet radiation, which occurs at very high altitudes in the stratosphere. The presence of SMIF in the ice core sulfate indicates that the Toba eruption injected material to altitudes exceeding 45 kilometers. To reach such heights, the eruption must have been extraordinarily powerful. The force required to propel material that high comes from the explosive expansion of volcanic gases. As magma rises and pressure decreases, dissolved gases separate from the liquid rock, forming bubbles. When the magma reaches the surface, the sudden pressure drop causes these bubbles to expand violently. This expansion drives the eruption, fragmenting the magma into ash and propelling it upward. The height of the column also depends on the temperature and density of the erupted material. Hotter, less dense material rises higher. The Toba eruption ejected magma that was rich in volatiles, particularly water vapor and sulfur dioxide. These gases, when released, expanded rapidly, adding to the column's buoyancy and driving it higher. Once in the stratosphere, the volcanic material encountered a different environment. The stratosphere is characterized by stable horizontal winds and minimal vertical mixing. Unlike the troposphere, where weather systems cause air to rise and fall, the stratosphere is relatively calm. This stability means that particles injected into the stratosphere can remain aloft for extended periods. The high-altitude winds, known as the stratospheric circulation, carry the material around the globe. The most significant component of the volcanic material, in terms of climate impact, was sulfur dioxide gas. Sulfur dioxide does not remain as a gas for long. In the stratosphere, it reacts with water vapor to form sulfuric acid. This acid condenses into tiny liquid droplets, creating a cloud of sulfate aerosols. These aerosols are extremely small, typically less than 1 micrometer in diameter, and they remain suspended in the air. The sulfate aerosol cloud spreads horizontally through the stratosphere, carried by the high-altitude winds. Within months, the cloud can encircle the globe. The aerosols remain aloft for several years, gradually settling back to the surface. During this time, they have a significant effect on the Earth's climate. The aerosols act like a mirror, reflecting incoming solar radiation back into space. Sunlight that would normally reach the Earth's surface and warm the ground is instead scattered back into space by the aerosol particles. This reduces the amount of solar energy reaching the surface, causing temperatures to drop. The cooling effect is most pronounced in the first few years after the eruption, when the aerosol concentration is highest. As the aerosols gradually settle out of the atmosphere, the cooling effect diminishes. The chemical signature in the Antarctic ice cores confirms that the Toba eruption injected sulfur dioxide to very high altitudes. The high altitude ensured that the sulfate aerosols remained in the stratosphere for an extended period, maximizing their climate impact. The eruption plume did not just reach the stratosphere, it penetrated deep into it, ensuring rapid and widespread distribution of volcanic material. The height of the Toba eruption column was one of the factors that made the eruption so consequential. A lower eruption might have injected material only into the troposphere, where it would have been removed by precipitation within weeks. But the Toba eruption breached the stratosphere, ensuring that the volcanic material would remain aloft for years, spreading across the planet and altering the climate on a global scale. The ash ejected by the Toba eruption did not remain confined to the vicinity of the volcano. Much of it was carried thousands of kilometers from the source, settling in layers that can still be detected today. These ash deposits provide a record of the eruption's reach and offer a unique tool for dating and correlating events across different regions. The erupted material is known as the youngest Toba tuff, or YTT. Close to the volcano, the ash deposits are thick. In some areas, the layer is several meters deep. As distance from the source increases, the thickness of the deposit decreases. But even at great distances, the ash can be detected, often as a microscopic layer embedded in sediments. The Indian subcontinent, located approximately 3,000 kilometers from Toba, was blanketed in ash. The layer is estimated to be around 5 centimeters thick. This may not sound like much, but 5 centimeters of volcanic ash covering an entire subcontinent represents an enormous volume of material. The ash would have covered vegetation, contaminated water sources, and disrupted ecosystems. For human populations living in the region, the immediate aftermath of the eruption would have been catastrophic. Beyond the Indian subcontinent, Toba ash has been found in marine sediment cores from the Indian Ocean, the Arabian Sea, and the South China Sea. These cores, drilled from the ocean floor, preserve a continuous record of sediment deposition over thousands of years. Within these sediments, there is a distinct layer of volcanic ash that dates to approximately 74,000 years ago. Chemical analysis of the ash confirms that it originated from the Toba eruption. The ash consists of tiny glass shards, fragments of magma that were rapidly cooled as they were ejected from the volcano. Each shard has a unique chemical composition, like a fingerprint, that can be matched to the source volcano. The most remarkable aspect of the Toba ash distribution is how far it travelled. Microscopic ash particles, known as cryptotephra, have been found at sites thousands of kilometers from Sumatra. Cryptotephra consists of glass shards so small that they are invisible to the naked eye. These particles can be transported vast distances by high-altitude winds before settling back to the surface. Scientists have identified Toba cryptotephra at Pinnacle Point, an archaeological site on the south coast of South Africa. Pinnacle Point is approximately 9,000 kilometers from Toba. The discovery of Toba ash at this site was significant because it provided a precise chronological marker. The ash layer could be dated with high accuracy, allowing researchers to align the archaeological record at Pinnacle Point with the timing of the eruption. Similarly, Toba ash has been found in the sediments of Lake Malawi, a large freshwater lake in East Africa. Lake Malawi is more than 7,000 kilometers from Toba. The sediment cores from the lake contain a thin layer of volcanic ash that matches the chemical signature of the youngest Toba tuff. The presence of this ash layer in the lake sediments provides a synchronous marker that can be used to correlate climate and environmental records across different regions. The widespread distribution of the Toba ash is important for several reasons. First, it confirms the scale of the eruption. An eruption that deposits measurable ash 9,000 kilometers from the source is extraordinarily powerful. Second, the ash layer provides a unique chronological tool. Because the eruption occurred at a specific point in time, the ash layer acts as an isochron, a horizon of the same age across different locations. This allows researchers to synchronize records from different parts of the world, aligning paleoclimate data, archaeological findings, and genetic studies with a common timeline. The ash layer also provides insight into atmospheric circulation patterns during the late Pleistocene. The distribution of ash reflects the pathways of high-altitude winds. The fact that ash reached South Africa and East Africa suggests that the eruption column penetrated high into the stratosphere, where the material was carried by the stratospheric circulation. The patterns of ash deposition can be used to reconstruct the atmospheric conditions at the time of the eruption. For the people living in these regions 74,000 years ago, the arrival of the ash would have been sudden and disorienting. The sky would have darkened as the ash cloud passed overhead. Fine ash would have rained down, covering the landscape in a thin, grey layer. The ash itself would not have been immediately lethal, but its presence would have signalled a profound disruption. The ash would have contaminated water sources, making them undrinkable. It would have coated vegetation, making it inedible for herbivores. The ecosystems that supported human populations would have been stressed, setting the stage for the more profound and long-lasting effects of the volcanic winter that was to follow. The ash layer from the Toba eruption is a geological signature, a marker left by one of the most powerful volcanic events in recent Earth history. It connects sites thousands of kilometers apart, providing a common thread that links the fates of distant human populations. The ash is a reminder that the Earth's systems are interconnected, and that events on one side of the planet can have consequences that ripple across continents and oceans. The youngest Toba tuff layer represents something remarkable in geological and archaeological science. It is a moment in time, preserved across continents and oceans, a horizon that marks the same instant in different places, separated by thousands of kilometers. In the language of geology, this is called an isochron, from the Greek words meaning equal time. Isochrons are rare and valuable. Most geological processes occur gradually, over long periods. Sediments accumulate slowly, landscapes erode incrementally. Climate shifts develop over centuries or millennia, but volcanic eruptions are instantaneous events on the geological timescale. A super-eruption like Toba ejects material that falls to Earth within days or weeks. The resulting ash layer, when preserved in sediments, provides a marker that can be dated with precision. The value of the Toba ash layer lies in its ability to synchronize records from different locations. Before the identification of the YTT layer in various sites, researchers studying climate change in East Africa, human migration patterns in South Asia, or genetic diversity in modern populations were working with separate chronologies. Each study had its own dating methods, its own uncertainties. Aligning these different records was difficult. The discovery of Toba ash at sites across Africa, Asia, and in ocean sediments changed this. The ash layer could be identified by its unique chemical composition. Volcanic glass from different eruptions has different concentrations of elements like silica, potassium, and titanium. These concentrations form a chemical fingerprint. When researchers find volcanic glass shards in sediments, they can analyze the chemical composition and match it to a specific eruption. At Pinnacle Point in South Africa, archaeologists were studying layers of sediment that contained stone tools and evidence of early human occupation. Within these layers, they found microscopic glass shards. Chemical analysis revealed that these shards matched the composition of the youngest Toba tuff. The discovery meant that the archaeological layers at Pinnacle Point could be directly linked to the timing of the Toba eruption, approximately 74,000 years ago. In Lake Malawi, sediment cores preserve a continuous record of environmental conditions over hundreds of thousands of years. Each layer of sediment corresponds to a specific time period. Scientists analyze pollen grains, chemical isotopes, and other indicators preserved in the sediment to reconstruct past climates. Within one of these cores, researchers found a thin layer containing Toba ash. This layer provided a precise time marker, allowing them to align the Lake Malawi climate record with the date of the eruption. The same process has been carried out at sites across the Indian Ocean, the Arabian Sea, and the South China Sea. Marine sediment cores from these regions contain the Toba ash layer, confirming that the eruption deposited material across this vast area. Each of these cores can now be dated relative to the eruption, creating a network of synchronized records. This synchronization has important implications for understanding human history. Genetic studies of modern human populations suggest that there was a reduction in genetic diversity sometime during the late Pleistocene. This reduction, known as a population bottleneck, indicates that the effective breeding population of humans decreased significantly at some point. The timing of this bottleneck has been debated. Some studies place it around 74,000 years ago, coinciding with the Toba eruption. Other studies suggest different dates. The Toba ash layer provides a way to test these hypotheses. If the genetic bottleneck occurred at the same time as the eruption, then archaeological sites from that period should show evidence of population stress or decline. Researchers can examine sites that contain the Toba ash layer and look for changes in human activity before and after the eruption. Do stone tools become less diverse, suggesting smaller populations? Do sites become abandoned? Or do human populations persist, showing continuity across the eruption event? The isochron also allows researchers to correlate climate records with genetic and archaeological data. Climate models can simulate the effects of the Toba eruption on global temperatures and precipitation. These models produce predictions about which regions would have experienced the most severe cooling and which might have been buffered from the worst effects. By comparing these predictions with paleoclimate records aligned to the Toba ash layer, scientists can test the accuracy of the models. The precision of the isochron is remarkable. Radiocarbon dating and other chronological methods have uncertainties, often on the order of hundreds or thousands of years. But the Toba ash layer is instantaneous. It marks a single event. When researchers find the ash in two different locations, they know that the sediments at that level were deposited at the same time. This precision transforms the study of the late Pleistocene, providing a framework for understanding events that occurred tens of thousands of years ago. The ash layer is also a reminder of the interconnectedness of Earth's systems. An eruption in Indonesia deposited ash in South Africa. The same volcanic gases that formed aerosols in the stratosphere above Sumatra were carried by winds to Antarctica, where they were trapped in ice. The climate effects of the eruption were felt globally, affecting ecosystems and human populations thousands of kilometers from the source. The Toba isochron is a thread that connects distant places and distant times. It is a moment frozen in geological layers, a marker that allows us to reconstruct the past with unusual clarity. The ash itself is inert, just microscopic fragments of volcanic glass, but the information it carries, the connections it enables, have transformed our understanding of a critical period in human history. The ash that fell from the Toba eruption settled relatively quickly. Within weeks, most of the coarser particles had returned to the surface, but the true climatic threat was not the ash. It was the gases, particularly sulfur dioxide, that the eruption injected into the stratosphere. Sulfur dioxide is a colorless gas with a sharp, irritating odor. It is released during volcanic eruptions when sulfur-bearing minerals in the magma decompose under the intense heat. The amount of sulfur dioxide released depends on the composition of the magma and the size of the eruption. For the Toba eruption, estimates of the total sulfur dioxide released range from 1,800 to 3,600 parts per million by weight of the erupted magma. In absolute terms, this translates to a release of between 200 and 2,000 teragrams of sulfur dioxide. A teragram is 1 trillion grams, or 1 million metric tons. To put this in perspective, modern human activities release approximately 100 teragrams of sulfur dioxide into the atmosphere each year, primarily from burning fossil fuels. The Toba eruption released between 2 and 20 times the annual human emission, all at once, and injected it directly into the stratosphere. In the lower atmosphere, sulfur dioxide is removed relatively quickly by rainfall, Rain dissolves the gas, forming sulfurous acid, which then falls to the surface. This is why most volcanic eruptions, even large ones, have limited long-term climate effects. The sulfur dioxide is washed out of the atmosphere within days or weeks, but the stratosphere is different. The stratosphere begins at an altitude of approximately 10 to 15 kilometers and extends to about 50 kilometers. Unlike the troposphere below, where weather occurs and air mixes vertically, the stratosphere is stable. There is minimal vertical movement and no significant precipitation. Material that enters the stratosphere can remain aloft for years. When sulfur dioxide reaches the stratosphere, it undergoes a chemical transformation. The gas reacts with water vapor, a process that produces sulfuric acid. Sulfuric acid is a liquid at the temperatures found in the stratosphere, approximately -50 to -80 degrees Celsius. The acid condenses into tiny droplets, typically less than 1 micrometer in diameter. These droplets are called sulfate aerosols. The formation of sulfate aerosols is not instantaneous. It takes weeks to months for the sulfur dioxide to fully convert to sulfuric acid and condense into aerosols. During this time, the gas and the forming aerosols are carried by stratospheric winds. The stratosphere has a general circulation pattern driven by temperature differences between the equator and the poles. Air rises in the tropics, moves poleward at high altitudes, and descends at mid-latitudes. This circulation spreads volcanic material globally. The Toba eruption occurred at a low latitude, approximately 2 degrees north of the equator. This location is significant because tropical eruptions inject material into the ascending branch of the stratospheric circulation. The material is carried upward and then spreads both northward and southward, ensuring distribution across both hemispheres. Within months of the eruption, the sulfate aerosol cloud would have encircled the planet. The aerosols are highly reflective. They scatter incoming solar radiation back into space. Sunlight that would normally pass through the atmosphere and warm the Earth's surface is instead reflected away. This scattering is most effective for visible and near ultraviolet wavelengths, which make up a large portion of the solar spectrum. The result is a reduction in the amount of solar energy reaching the surface, leading to cooling. The cooling effect is not immediate. It takes time for the aerosols to form and spread, but once the aerosol cloud is fully developed, the cooling begins. Climate models estimate that the temperature drop depends on the total mass of sulfur dioxide released and the resulting aerosol distribution. For the Toba eruption, different emission scenarios produce different cooling magnitudes. In scenarios with lower sulfur emissions, around 200 teragrams of sulfur dioxide. Climate models calculate a global mean cooling of approximately 2.3 degrees Celsius, with an uncertainty of about 0.4 degrees. For higher emission scenarios, around 2,000 teragrams, the cooling reaches approximately 4.1 degrees Celsius, with an uncertainty of about 0.3 degrees. These numbers represent the maximum cooling, which occurs 1 to 3 years after the eruption. The cooling then gradually diminishes as the aerosols settle out of the stratosphere. Most models suggest that the temperature anomaly returns to less than 1 degree Celsius within 3 to 6 years after the eruption. However, the initial cooling phase, lasting 6 to 10 years, would have been a period of significant climatic stress. The sulfate aerosols do not just cause cooling, they also affect the amount of light reaching the surface. Even if the temperature drop were modest, the scattering of sunlight by the aerosol cloud creates a dimming effect. The sky would appear hazy, and the intensity of sunlight would be reduced. This dimming has consequences for photosynthesis, the process by which plants convert sunlight into chemical energy. Photosynthesis requires a certain intensity of light. When light levels drop below a threshold, plant growth slows or stops. The aerosol cloud from the Toba eruption would have reduced light levels globally for several years. The dimming would have been most severe in the first few years, when the aerosol concentration was highest. During this time, plant productivity would have declined worldwide, disrupting food chains and ecosystems. The transformation of sulfur dioxide into sulfate aerosols is a slow, invisible process. The gas itself is transparent. The aerosols are too small to see individually, but collectively they form a veil that alters the Earth's energy balance. This veil, spread across the stratosphere by high-altitude winds, persisted for years after the eruption, driving the volcanic winter that followed. The sulfate aerosol cloud formed by the Toba eruption acted as a barrier between the Earth and the Sun. This barrier did not block sunlight completely, but it scattered a significant portion of it back into space. The mechanism is straightforward. Aerosol particles in the stratosphere are comparable in size to the wavelength of visible light. When sunlight strikes these particles, some of it is absorbed, but most is scattered in different directions. A portion of this scattered light is redirected back towards space. The scattering efficiency depends on the size and composition of the aerosol particles. Sulfate aerosols are particularly effective scatterers because they are spherical and have a refractive index that causes strong interaction with light. The particles are also distributed over a large area and remain suspended at high altitudes, maximizing their interaction with incoming solar radiation. The amount of sunlight reflected depends on the total mass of aerosols in the stratosphere and their distribution. For the Toba eruption, estimates of sulfur dioxide emissions suggest that the aerosol cloud was substantial. Even at the lower end of emission estimates, the aerosol burden would have been sufficient to reduce incoming solar radiation by several percent. At the higher end, the reduction could have exceeded 10%. A reduction of a few percent may not sound significant, but the Earth's climate system is sensitive to changes in solar input. The global mean temperature is determined by the balance between incoming solar radiation and outgoing infrared radiation. When incoming radiation decreases, the surface cools. The cooling is not uniform. It varies by latitude, season, and local conditions. But the global average temperature drops. The cooling effect is most pronounced during the first few years after the eruption, when the aerosol concentration is highest. As the aerosols gradually settle out of the stratosphere, the cooling diminishes. The stratosphere has a residence time for particles of approximately 2 to 3 years, meaning that half of the aerosols will have settled out within that time. After 5 to 6 years, most of the aerosols are gone, and the temperature begins to recover. But the period of maximum cooling, lasting several years, would have had significant ecological consequences. Temperature affects many aspects of the environment. Growing seasons shorten when temperatures drop. Plants that are adapted to specific temperature ranges may be unable to survive. Animals that depend on these plants face food shortages. The cascading effects propagate through the ecosystem. The aerosol cloud also caused global dimming, a reduction in the amount of sunlight reaching the surface. Dimming is distinct from cooling. Even if the temperature remained constant, a reduction in light intensity would affect photosynthesis. Plants use light energy to convert carbon dioxide and water into sugars. This process is the foundation of most food chains. When light levels drop, photosynthesis slows. Studies of modern volcanic eruptions provide insight into the effects of aerosol clouds. The 1991 eruption of Mount Pinatubo in the Philippines injected approximately 20 teragrams of sulfur dioxide into the stratosphere. The resulting aerosol cloud spread globally, causing a measurable drop in temperature of about 0.5 degrees Celsius over the following 2 years. Satellite measurements showed that the amount of solar radiation reaching the surface decreased by several percent. Agricultural yields in some regions declined due to the reduced sunlight. The Toba eruption was an order of magnitude larger than Pinatubo. If Pinatubo, with its 20 teragrams of sulfur dioxide, caused measurable global effects, the Toba eruption, with emissions potentially exceeding 100 times that amount, would have had correspondingly greater impacts. The aerosol cloud from Toba would have affected the Earth's radiation balance for several years. During this time, the surface would have received less sunlight. The sky would have appeared milky or hazy, even on clear days. The intensity of sunlight would have been reduced, altering the visual environment. Shadows would have been less sharp. The light would have been diffuse, scattered by the aerosol particles. For ecosystems, the dimming would have been as significant as the cooling. Photosynthesis is sensitive to light intensity. When light levels drop below a certain threshold, known as the compensation point, plants cannot produce enough energy to sustain themselves. Growth stops, and plants begin to draw on stored reserves. If the dimming persists, plants die. The combination of cooling and dimming would have stressed ecosystems globally. Tropical regions, which normally receive abundant sunlight and warmth, would have experienced unprecedented conditions. Temperate regions, already subject to seasonal variations in temperature and light, would have faced extended periods of cold and dim conditions. High-latitude regions would have been least affected by the cooling, as they were already cold, but the dimming would still have reduced plant productivity during the growing season. The mirror in the sky, the sulfate aerosol cloud, was an invisible barrier. It did not block the sun, but it altered the flow of energy from the sun to the earth. This alteration, sustained over several years, drove the volcanic winter, a period of reduced temperatures and diminished sunlight that challenged life across the planet. Understanding the climate impact of the Toba eruption requires climate models. These models are mathematical representations of the Earth's climate system, incorporating the atmosphere, oceans, land surface, and ice sheets. The models solve equations that describe how energy and matter flow through the system. By adjusting the inputs, such as the amount of volcanic aerosols in the stratosphere, researchers can simulate the climate response to an eruption. For the Toba eruption, climate models have been run with different assumptions about the amount of sulfur dioxide released. The emissions are uncertain, with estimates ranging from 200 to 2,000 teragrams. This uncertainty reflects the difficulty of reconstructing past events from geological evidence. Different studies produce different estimates based on different methods and assumptions. Climate models are run separately for each emission scenario. The models start with pre-eruption conditions, then introduce the volcanic aerosols into the stratosphere. The aerosols are distributed according to atmospheric circulation patterns. The models then calculate how the climate system responds over time. For a lower emission scenario, with approximately 200 teragrams of sulfur dioxide, the models predict a maximum global mean cooling of about 2.3 degrees Celsius. This maximum occurs 1 to 3 years after the eruption. The uncertainty in this estimate is approximately 0.4 degrees Celsius, reflecting variations between different climate models and different assumptions about aerosol properties. For a higher emission scenario, with approximately 2,000 teragrams of sulfur dioxide, the models predict a maximum cooling of about 4.1 degrees Celsius, with an uncertainty of about 0.3 degrees Celsius. This larger cooling reflects the greater aerosol burden in the stratosphere. These global mean values are averages over the entire planet. The actual cooling varies by location. Land surfaces cool more than oceans because land has a lower heat capacity. High latitudes cool more than low latitudes in some seasons, but less in others, depending on factors like ice albedo feedback. Tropical regions experience less absolute cooling, but more relative cooling, as they are normally warm and stable. The duration of the cooling also varies. The most severe phase, when temperatures are at their lowest, lasts approximately 6 to 10 years. After this period, the aerosol concentration decreases as particles settle out of the stratosphere. Temperatures begin to recover, but the recovery is not immediate. Climate models suggest that it takes 3 to 6 years for the temperature anomaly to decrease to less than 1 degree Celsius. Some models also account for feedback mechanisms that could prolong the cooling. When temperatures drop, snow and ice cover increases. Snow and ice are highly reflective, bouncing sunlight back into space. This albedo feedback can amplify the initial cooling, maintaining lower temperatures even after the volcanic aerosols have dissipated. Ocean circulation can also play a role. Cooler surface temperatures can alter ocean currents, affecting heat transport and prolonging the temperature anomaly. The models also calculate the impact on precipitation. Volcanic aerosols affect not only temperature, but also atmospheric circulation patterns. The cooling can alter the distribution of atmospheric pressure, changing wind patterns and rainfall. For the Toba eruption, models predict a strong global precipitation anomaly. One of the most significant effects is on monsoon systems. Monsoons are seasonal wind patterns that bring heavy rainfall to certain regions. The Asian monsoon, which affects India and Southeast Asia, is driven by temperature differences between the land and ocean. When the land heats up during summer, air rises, drawing in moist air from the ocean. This causes heavy rainfall during the monsoon season. Volcanic cooling reduces the temperature difference between land and ocean. The land does not heat up as much, weakening the pressure gradient that drives the monsoon. Climate models predict that the Toba eruption would have disrupted the Indian monsoon, reducing rainfall across the Indian subcontinent. Similar effects are predicted for the West African monsoon. The reduction in rainfall would have had severe consequences for ecosystems and human populations in these regions. Reduced rainfall means less water available for plants and animals. Rivers and lakes could shrink or dry up. Vegetation would suffer, leading to declines in herbivore populations. For human hunter-gatherers, who depended on reliable water sources and the animals that gathered around them, the disruption of monsoon patterns would have compounded the stress caused by cooling and dimming. The models also predict regional differences in the severity of the impact. Some areas, particularly coastal regions and tropical islands, would have been buffered by the moderating influence of the ocean. Others, particularly inland areas at mid-latitudes, would have experienced more severe cooling and drying. The distribution of impacts would have determined which human populations face the greatest challenges. The mathematics of climate modelling provides a framework for understanding the Toba eruption's impact. The models are not perfect. They are simplifications of a complex system, and they depend on assumptions about aerosol properties, atmospheric circulation, and feedback mechanisms. But they offer the best available tool for reconstructing the climate of 74,000 years ago. The results consistently show that the eruption would have caused significant global cooling and disruption of precipitation patterns, with the most severe effects lasting approximately 6 to 10 years. The primary threat posed by the Toba eruption was not the temperature drop, significant though it was. The more profound challenge was the disruption of photosynthesis. Photosynthesis is the process by which plants convert light energy into chemical energy, producing the sugars that fuel their growth and ultimately the entire food chain. The process requires three basic inputs: light, carbon dioxide, and water. Plants absorb sunlight through pigments, primarily chlorophyll, located in their leaves. The light energy drives a series of chemical reactions that split water molecules and combine the resulting hydrogen with carbon dioxide to produce glucose. Oxygen is released as a byproduct. Photosynthesis is sensitive to light intensity. There is a minimum threshold, called the light compensation point, below which the plant cannot produce enough energy to sustain itself. Below this point, the plant consumes more energy through respiration than it produces through photosynthesis. If light levels remain below the compensation point for an extended period, the plant will exhaust its stored reserves and die. The sulfate aerosol cloud from the Toba eruption scattered incoming sunlight, reducing the intensity of light reaching the Earth's surface. The reduction was substantial, potentially exceeding 10% in regions directly beneath the densest parts of the aerosol cloud. This dimming would have pushed some ecosystems below the light compensation point, causing widespread plant die-off. The effects would have been most severe in regions that were already marginal. Forests at high latitudes, which receive limited sunlight during winter, would have been vulnerable. Grasslands in semi-arid regions where plants are adapted to specific light and moisture levels would have struggled. Even tropical forests, which normally receive abundant sunlight, would have experienced stress. As plants died, the consequences cascaded through the ecosystem. Herbivores, which depend on plants for food, would have faced declining food availability. Populations of grazers and browsers would have decreased. Predators, which depend on herbivores, would have faced secondary food shortages. The disruption propagated up the food chain. For early human populations who were hunter-gatherers, the collapse of plant productivity was a direct threat. Humans are omnivores, consuming both plant and animal foods. When plant resources decline, humans can shift their diet toward animal foods. But when the entire ecosystem is stressed, animal populations also decline, eliminating this alternative. Archaeological evidence suggests that late Pleistocene humans had diverse diets. They gathered roots, tubers, fruits, and nuts. They hunted large and small game. They fished in rivers and foraged along coastlines. But all of these resources ultimately depend on primary productivity, the growth of plants. When photosynthesis is disrupted, the entire food web is undermined. The dimming caused by the aerosol cloud would have been persistent. Unlike seasonal changes in sunlight, which occur predictably each year, the volcanic dimming would have lasted for several years, spanning multiple growing seasons. Plants adapted to specific light conditions would have been unable to adjust. Annual plants, which complete their life cycle in a single year, might have failed to produce seeds. Perennial plants might have survived in a dormant state, but they would not have grown or reproduced. The geographical distribution of the dimming would have varied. Regions beneath the densest parts of the aerosol cloud would have experienced the greatest reduction in light, but even regions with less dimming would have faced challenges. The aerosol cloud was global, meaning that no region escaped entirely. The severity of the impact depended on local conditions, including the baseline light levels, the types of vegetation present, and the availability of alternative food sources. Some ecosystems would have been more resilient than others. Coastal regions, with access to marine resources, would have been buffered from the worst effects of terrestrial ecosystem collapse. Marine ecosystems, particularly in shallow waters where light penetrates, would also have been affected by dimming, but the impact would have been less severe than on land. Phytoplankton, the microscopic plants that form the base of the marine food web, can tolerate lower light levels than terrestrial plants. Inland regions, particularly those that were already arid or semi-arid, would have faced compounded challenges. The disruption of monsoon patterns would have reduced rainfall, stressing vegetation. The dimming would have further reduced plant growth. The combination of drought and reduced light would have been devastating for ecosystems that depended on seasonal rainfall to sustain plant growth during the brief wet season. The failure of photosynthesis was the mechanism by which the volcanic winter translated into famine. The temperature drop made conditions colder, but cold alone does not eliminate food. The disruption of rainfall made conditions drier, but drought alone can be survived by moving to areas with water. The dimming, however, attacked the foundation of the food supply. Without light, plants cannot grow. Without plants, herbivores cannot eat. Without herbivores, humans cannot hunt. The volcanic winter was fundamentally a starvation event, driven by the collapse of primary productivity across the planet. Water is as essential to life as light. For ecosystems in the tropics and subtropics, the arrival of seasonal rains determines the rhythm of the year. These rains are delivered by monsoon systems, large-scale wind patterns that shift with the seasons and bring moisture from the oceans to the land. The disruption of these systems by the Toba eruption would have had consequences as severe as the dimming of sunlight. Monsoons are driven by temperature differences between land and ocean. During summer months, the land surface heats more rapidly than the ocean. Warm air over the land rises, creating a region of low pressure. Air from over the ocean, which is cooler and denser, flows toward the land to replace the rising air. This air is laden with moisture. As it moves inland and rises over mountains or heated land surfaces, the moisture condenses, producing heavy rainfall. The Asian monsoon is one of the largest and most important of these systems. It affects the Indian subcontinent, Southeast Asia, and parts of East Asia. Billions of people today depend on monsoon rains for agriculture. 74,000 years ago, the ecosystems and human populations of these regions were equally dependent on the seasonal delivery of water. The sulfate aerosol cloud from the Toba eruption altered the temperature balance that drives monsoons. The aerosols reflected sunlight back into space, reducing the amount of solar energy reaching the land surface. The land did not heat as much as it normally would during the summer months. The temperature difference between land and ocean decreased. The pressure gradient that drives the monsoon circulation weakened. Climate models that simulate the Toba eruption predict significant disruption to monsoon systems. For the Indian monsoon, models show a reduction in rainfall of 20 to 40% during the years following the eruption. The West African monsoon, which brings seasonal rains to the Sahel and parts of West Africa, also shows weakening in the models. The reduction in rainfall is not uniform across the entire monsoon region. Some areas experience greater reductions than others, depending on local topography and atmospheric circulation patterns. The consequences of reduced monsoon rainfall would have been immediate and severe. In regions that depend on seasonal rains, vegetation is adapted to survive dry periods by storing water or going dormant. But these adaptations assume that the rains will arrive on schedule. When the monsoon fails, or when it delivers significantly less rainfall than normal, vegetation cannot complete its growth cycle. Annual grasses fail to produce seeds. Trees do not leaf out fully. Water sources that normally replenish during the wet season remain depleted. For animal populations, the failure of the monsoon would have meant reduced food and water availability. Herbivores that depend on fresh vegetation during the wet season would have faced shortages. Many would have died. Others would have migrated in search of better conditions, potentially bringing them into conflict with other populations or into unfamiliar territories where they were more vulnerable to predators. For human populations, the monsoon failure compounded the challenges already posed by cooling and dimming. Humans in monsoon-dependent regions would have relied on the seasonal abundance of resources that the rains brought. During the wet season, rivers would flow, waterholes would fill, and vegetation would flourish. Game animals would congregate at water sources. Plant foods would be abundant. This seasonal pulse of productivity would have been critical for survival during the dry season. The disruption of the monsoon would have eliminated this seasonal pulse. Rivers that normally flowed during the wet season might have remained dry or carried only a trickle of water. Waterholes might not have refilled. Vegetation would have been sparse and stressed. Game animals would have been scarce, having died or moved elsewhere. The landscape would have resembled a prolonged dry season, extending for years rather than months. Archaeological evidence from the Indian subcontinent provides some insight into conditions during the Toba period. Sites that were occupied before the eruption show evidence of human activity: stone tools, hearths, animal bones. After the eruption, some sites show continuity of occupation, suggesting that humans persisted. But the character of the evidence changes. Tool assemblages show signs of stress or adaptation. The types of animals hunted may shift toward more drought-tolerant species. These subtle changes in the archaeological record suggest that humans were adapting to altered environmental conditions. In northwestern Ethiopia, evidence from the Shinfa Matema site tells a similar story. This site is located along a tributary of the Blue Nile River. Today, the region experiences strong seasonal aridity, with a pronounced dry season. Analysis of isotopes in fossil mammal teeth and ostrich eggshells from the site confirms that this seasonal pattern existed 74,000 years ago as well. The presence of Toba ash at the site confirms that humans were living there during and after the eruption. The adaptation strategy at Shinfa Matema was focused on rivers. During the dry season, when the tributary slowed or stopped flowing, the remaining waterholes became critical resources. These pools concentrated fish. They also attracted terrestrial animals that needed to drink. Humans at the site shifted their subsistence strategy to focus intensively on these riverine resources. They harvested fish from the shrinking pools. They hunted animals that came to drink. This strategy was effective because it exploited a predictable concentration of resources. Even during severe drought, rivers and their associated waterholes provided refugia. The Blue Nile system, fed by highland rains, continued to flow even when local rainfall failed. The tributary system created seasonal bottlenecks where resources could be harvested efficiently. The disruption of monsoon systems by the Toba eruption would have made such adaptations necessary across much of the tropics and subtropics. Humans could not rely on the normal seasonal patterns. They needed to identify and exploit resources that remained available during prolonged dry conditions. Rivers, lakes, and coastlines became critical. These were the places where water and food could still be found, even when the land between them turned arid and lifeless. The monsoons did not fail permanently. After the volcanic aerosols settled out of the stratosphere and temperatures began to recover, the monsoon systems would have gradually returned to their normal patterns. But the years of disruption, coinciding with the period of maximum cooling and dimming, would have tested the adaptability of every species that depended on seasonal rainfall. For humans, the challenge was to survive long enough for the rains to return. The scale of the Toba eruption and the severity of its predicted climatic effects led to a compelling hypothesis. If the volcanic winter caused global ecological stress, if plant growth collapsed and animal populations declined, then surely human populations would have been affected as well. Perhaps severely, perhaps catastrophically. In the late 1990s and early 2000s, anthropologist Stanley Ambrose and others proposed what became known as the Toba catastrophe theory. The hypothesis was straightforward. The Toba eruption caused a drastic reduction in the global human population. The effective breeding population, the number of individuals contributing to the next generation, dropped to between 3,000 and 10,000 individuals. This reduction pushed the species to the brink of extinction. The survivors were fragmented into small, isolated groups scattered across Africa and possibly other regions. These groups faced heightened risk of local extinction. Only through chance and adaptation did humanity survive. The theory was grounded in genetics. Studies of human genetic diversity had revealed a puzzling pattern. When geneticists compare the DNA of people from different populations around the world, they find that humans are remarkably similar. The genetic differences between any two humans are small compared to the differences found in other species, even other primates. Chimpanzees, for example, show much greater genetic diversity than humans, despite having a smaller total population. This low genetic diversity suggested that humans had passed through a population bottleneck at some point in the past. A bottleneck occurs when a population is suddenly reduced to a small number of individuals. The reduction eliminates much of the genetic variation present in the original population. When the population expands again, it carries forward only the limited genetic variation present in the bottleneck survivors. Population bottlenecks have predictable genetic signatures. One is reduced heterozygosity, the proportion of genetic loci where individuals carry two different versions of a gene. Another is altered allele frequency distributions, with some genetic variants becoming more common and others disappearing entirely. Genetic drift, the random change in gene frequencies, becomes stronger in small populations, accelerating these changes. The timing of the human genetic bottleneck was debated, but some genetic studies suggested it occurred around 70 to 80,000 years ago. This coincided roughly with the date of the Toba eruption. The correlation was suggestive. Could the eruption have been the cause of the bottleneck? The Toba catastrophe theory proposed a mechanism. The volcanic winter disrupted ecosystems globally. Food became scarce. Human populations, which were already relatively small, declined sharply. Many groups went extinct entirely. The survivors were concentrated in a few refugia, places where ecological conditions remained tolerable. These refugia might have been in equatorial Africa, where the climate was more stable, or along coastlines, where marine resources provided an alternative food source. The fragmentation of the human population into small, isolated groups would have intensified genetic drift. In each group, random changes in gene frequencies would have occurred. Some genetic variants would have been lost purely by chance. Others would have increased in frequency. Over time, the isolated groups would have become genetically distinct from one another. The theory also suggested that the bottleneck might have accelerated human evolution. In small populations, natural selection can act more efficiently. Beneficial mutations, if they occur, can spread more quickly. Slightly deleterious mutations can also become fixed, increasing the genetic load, but they might be compensated for by other changes. The intense selective pressure imposed by the harsh post-eruption environment might have favored cognitive and behavioral innovations. Groups that developed more sophisticated tool technologies, more efficient foraging strategies, or more cooperative social structures would have had higher survival rates. Ambrose proposed that the Toba event not only reduced human population size, but also drove the differentiation of modern human groups. The isolation and selective pressures could have contributed to the emergence of the distinct behavioral and cultural characteristics seen in modern Homo sapiens. The recovery from the bottleneck, beginning around 60,000 years ago when the climate warmed, might have set the stage for the successful expansion of modern humans out of Africa. The Toba catastrophe theory was dramatic. It offered a clear, simple explanation for several puzzling observations: the low genetic diversity of modern humans, the timing of the genetic bottleneck, and the emergence of behavioral modernity. It connected a known geological event with anthropological and genetic evidence. For a time, it was widely discussed and cited. But science advances through scrutiny. Hypotheses must be tested against new evidence. As more data became available, from paleoclimate records, archaeological excavations, and refined genetic analyses, the Toba catastrophe theory faced challenges. The emerging picture was more complex than a simple global catastrophe. The eruption was real. Its climatic effects were significant, but whether it nearly exterminated humanity, that claim required careful examination. The logic of the bottleneck hypothesis rests on population genetics. When a population is large, genetic diversity is maintained. Random changes in gene frequencies, known as genetic drift, occur, but their effects are small. Natural selection can act on beneficial or harmful mutations, but the large population provides a buffer. Rare genetic variants can persist for many generations. When a population suddenly shrinks, the dynamics change. Genetic drift becomes the dominant force. In a small population, random events have outsized effects. If an individual carrying a rare genetic variant happens to have more offspring than others, that variant can quickly become more common. Conversely, if an individual carrying a variant fails to reproduce, that variant can disappear from the population entirely. This process is called a founder effect, when a new population is established by a small number of individuals. The genetic diversity of the new population is limited to whatever variants the founders happen to carry. Much of the diversity present in the original population is lost. The Toba catastrophe theory proposed that the human population experienced an extreme founder effect, with only a few thousand individuals surviving to pass on their genes. The genetic evidence for a human population bottleneck comes from several sources. One is the distribution of mutations across the genome. When populations are large and stable, mutations accumulate at a steady rate. The number of differences between any two individuals reflects how long ago their lineages diverged. When a bottleneck occurs, the pattern changes. The time to the most recent common ancestor for many genetic loci shifts to the time of the bottleneck, creating a characteristic signature. Studies of mitochondrial DNA, which is inherited maternally, suggest that all modern humans share a common maternal ancestor who lived approximately 150 to 200,000 years ago. This individual, often called mitochondrial Eve, was not the only woman alive at the time, but she is the one whose mitochondrial lineage survived to the present. Similar analyses of the Y chromosome, inherited paternally, identify a common paternal ancestor, Y chromosomal Adam, who lived somewhat more recently, around 200 to 300,000 years ago. These dates do not directly correspond to a bottleneck at 74,000 years ago. However, other genetic evidence does point to a more recent event. Some studies of autosomal DNA, the genetic material inherited from both parents, identify a reduction in genetic diversity that could correspond to a bottleneck in the late Pleistocene. The estimated timing varies depending on the methods used and the assumptions made about mutation rates and generation times. Some genetic analyses place the bottleneck around 50,000 years ago. Others suggest dates closer to 74,000 years ago. Still others propose that the bottleneck was not a single event but a prolonged period of low population size spanning tens of thousands of years. The uncertainty reflects the difficulty of extracting precise historical information from genetic data. The fragmentation of the human population during a bottleneck would have additional consequences. If survivors were isolated in separate refugia, each group would have undergone independent genetic drift. Over time, the groups would have diverged genetically. When populations expanded and came back into contact, they would have been genetically distinct, though still capable of interbreeding. This scenario is consistent with some observations of modern human genetic diversity. Populations in Africa show higher genetic diversity than populations outside Africa. This pattern suggests that African populations maintained larger sizes or experienced less severe bottlenecks. Populations outside Africa, which are thought to descend from a small group that left Africa around 60,000 years ago, show reduced diversity, consistent with a founder effect during the out-of-Africa migration. The Toba catastrophe theory attempted to link this genetic pattern to a specific environmental event. The eruption occurred at 74,000 years ago. The genetic bottleneck occurred sometime in the late Pleistocene, possibly around the same time. The theory proposed that the eruption caused the bottleneck. However, the connection is not straightforward. Genetic bottlenecks can be caused by many factors: disease, climate change, competition with other species, or simple population dynamics. The timing of the genetic bottleneck, as estimated from genetic data, has considerable uncertainty. A date of 50,000 years ago is not the same as 74,000 years ago. The difference of 24,000 years is longer than the entire span of recorded human history. Moreover, some genetic studies suggest that the primary bottleneck affecting modern human populations occurred much earlier, around 1 million years ago, corresponding to a different period of environmental stress. If the major bottleneck predated Toba by hundreds of thousands of years, then the eruption, however severe, did not cause the genetic pattern we observe today. The genetic evidence is complex and sometimes contradictory. Different genetic loci tell different stories reflecting different aspects of human demographic history. The population size of humans has fluctuated many times over the last million years. Bottlenecks, expansions, and migrations have left overlapping signatures in the genome. Disentangling these signatures to identify the effects of a specific event like the Toba eruption is challenging. Genetics alone cannot prove or disprove the Toba catastrophe theory. The genetic data must be considered alongside other lines of evidence: paleoclimate records, archaeological findings, and climate modelling. As more data became available, the simple narrative of a global catastrophe at 74,000 years ago became harder to sustain. The Toba eruption was real, the climatic effects were significant, but the question was whether these effects translated into a near-extinction event for Homo sapiens. The answer, increasingly, appeared to be no. The first line of evidence came from paleoclimate records. If the eruption caused a severe global cooling lasting a decade or more, this should be detectable in climate proxies, ice cores, ocean sediments, lake sediments, and cave deposits. These archives preserve chemical and biological indicators of past temperatures and environmental conditions. Antarctic ice cores show the sulfate peak corresponding to the Toba eruption. The peak is sharp and distinct, confirming that volcanic material reached the Antarctic ice sheet. The sulfur isotope signature indicates a tropical source and high-altitude injection, consistent with the Toba eruption. However, the ice cores do not show a corresponding dramatic drop in temperature. Temperature is inferred from the ratio of oxygen isotopes in the ice. The ratio shifts with temperature because lighter and heavier isotopes of oxygen evaporate and condense at different rates. The ice core record from around 74,000 years ago shows some variability, but not a clear, sustained cooling event that stands out from the background climate fluctuations of the late Pleistocene. Ocean sediment cores tell a similar story. These cores preserve a record of sea surface temperatures inferred from the chemical composition of microscopic shells of marine organisms called foraminifera. The shells incorporate oxygen isotopes and other elements in ratios that depend on the temperature of the water. When researchers analyze sediment cores from around 74,000 years ago, they do not find strong evidence for a dramatic, sustained global cooling event. The most significant paleoclimate evidence comes from Africa. Africa was the center of the human population during the late Pleistocene. If the Toba eruption caused a population bottleneck, the effects should be most evident in African climate records. The Lake Malawi sediment cores are particularly important. Lake Malawi is a large freshwater lake in East Africa, and its sediments preserve a continuous record spanning hundreds of thousands of years. Researchers analyzing the Lake Malawi cores identified the Toba ash layer, confirming that the eruption affected this region. They then examined the sediments immediately above and below the ash layer, looking for evidence of environmental change. They analyzed pollen grains, which indicate the types of vegetation present. They measured chemical indicators of temperature and aridity. They looked at charcoal abundance, which reflects fire frequency. The results were unexpected. The sediments showed no substantial change in temperature around the time of the eruption. Vegetation composition remained stable. There was no evidence of a catastrophic collapse of the ecosystem. The environment at Lake Malawi during and after the Toba eruption appears to have been similar to the environment before the eruption. East Africa, it seemed, was largely insulated from the worst effects of the volcanic winter. This finding is significant because East Africa was home to the largest populations of Homo sapiens during the late Pleistocene. If the core demographic reservoir of the species was in a region that did not experience catastrophic environmental change, then the species as a whole would not have been pushed to the brink of extinction. Other African climate records support this interpretation. Sediment cores from Lake Tanganyika and other sites show similar patterns. There is evidence for climate variability during the late Pleistocene, but no clear signal of a catastrophic event at 74,000 years ago. The climate in equatorial Africa appears to have been relatively stable, buffered perhaps by the proximity to large bodies of water or by atmospheric circulation patterns that delivered moisture even when monsoons elsewhere were disrupted. Archaeological evidence also challenges the catastrophe narrative. If the Toba eruption caused a drastic reduction in human populations, this should be visible in the archaeological record. Sites occupied before the eruption should show signs of abandonment or decline. The diversity of tool types should decrease, reflecting smaller, more isolated populations. The density of artifacts should drop. In some regions, the archaeological record is sparse, making it difficult to draw conclusions. But in a few key areas, the evidence is clear. The Jwalapuram site in southern India, for example, contains sediments with Toba ash. Stone tools are found both below and above the ash layer. The tools belong to the Middle Paleolithic tradition, characterized by specific methods of flaking stone to produce sharp edges. Importantly, the tool technologies below and above the ash layer are similar. There is continuity, not disruption. A similar pattern is seen at the Dahaba site in northern India. Here, stone tools of the Middle Paleolithic type are found throughout the sequence spanning the Toba eruption. The tools are made from locally available stone. The methods of manufacture do not change significantly. The presence of tools above the ash layer indicates that humans survived the ashfall and continue to live in the region. These findings suggest that human populations in India, close to the eruption source, were not wiped out. They faced significant environmental stress from the ashfall, which would have covered the landscape and disrupted local ecosystems. But they adapted and persisted. In other regions, the picture is more complex. Some sites show signs of abandonment or changes in occupation intensity around the time of the Toba eruption. But these changes could be due to many factors, including normal fluctuations in population density, shifts in resource availability unrelated to Toba, or changes in settlement patterns. The archaeological record is incomplete. Many sites from 74,000 years ago have been destroyed or buried. The absence of evidence is not evidence of absence, but the available evidence does not support a global catastrophe. Instead, it suggests regional variability. Some areas were severely affected, others were relatively stable. Human populations in some regions declined or moved. In other regions, they persisted. Lake Malawi lies in the East African Rift Valley, a geological feature created by the slow tearing apart of the African continent. The lake is long and narrow, stretching over 500 kilometers from north to south. It is deep, reaching depths of over 700 meters. The lake has existed for millions of years, and its sediments preserve a continuous record of environmental conditions over that time. Sediment accumulates on the lake floor at a steady rate. Each year, particles settle from the water column, clay and silt washed in by rivers, organic matter from decaying algae and plants, pollen grains blown in by the wind, and occasionally volcanic ash from distant eruptions. Over time, these layers compress and form a sediment column. By drilling into the lake floor and extracting a core, scientists can retrieve the sediment column and analyze it layer by layer. The Lake Malawi cores are among the most important paleoclimate records from Africa. They have been analysed extensively, with researchers examining multiple indicators to reconstruct past temperatures, rainfall, and vegetation. The cores span the last 140,000 years, covering several glacial-interglacial cycles. Within one of these cores, researchers identified a thin layer of volcanic ash. Chemical analysis of the ash confirmed that it originated from the Toba eruption. The glass shards in the ash have a distinctive chemical composition, matching the signature of the youngest Toba tuff. The presence of this ash layer provided a precise chronological marker, allowing researchers to align the Lake Malawi climate record with the date of the Toba eruption at 74,000 years ago. Having identified the ash layer, the researchers focused their attention on the sediments immediately before and after it. They wanted to determine whether the eruption had caused any detectable change in the environment around Lake Malawi. They employed several methods. First, they analysed pollen grains preserved in the sediment. Pollen is produced by plants and dispersed by wind or animals. Different plants produce pollen with distinctive shapes and surface textures. By identifying the types of pollen in each sediment layer, researchers can determine what plants were present in the region at that time. Changes in pollen assemblages indicate changes in vegetation, which in turn reflect changes in climate. The pollen record from Lake Malawi showed no significant change around the time of the Toba eruption. The types of plants represented in the pollen assemblages remained consistent. There was no shift from forest to grassland, or from grassland to desert, as might be expected if the climate had become significantly cooler or drier. The vegetation around the lake appears to have been stable. Second, the researchers analysed the abundance of charcoal particles in the sediment. Charcoal is produced by fires. The amount of charcoal in sediments reflects the frequency and intensity of fires in the surrounding landscape. Fire regimes are influenced by climate, particularly by temperature and moisture availability. In dry conditions, fires are more frequent. In wet conditions, fires are less common. The charcoal record from Lake Malawi showed no increase in fire activity around the time of the Toba eruption. This suggests that the region did not become significantly drier. If the eruption had disrupted the monsoon and caused prolonged drought, an increase in fire activity would be expected. The absence of such an increase indicates that moisture availability remained relatively stable. Third, the researchers examined chemical indicators of lake water conditions. The ratio of certain isotopes in the sediment reflects the balance between evaporation and rainfall. When evaporation exceeds rainfall, the lake becomes more concentrated in heavier isotopes. When rainfall exceeds evaporation, the lake becomes diluted. This isotope ratio provides an indicator of aridity. The isotope record from Lake Malawi showed normal variability around the time of the Toba eruption. There was no sustained shift toward more arid conditions. The lake's water balance appears to have remained stable. This is consistent with the pollen and charcoal evidence, all pointing to environmental continuity rather than catastrophic change. The stability of the Lake Malawi environment during the Toba event is significant for understanding human survival. East Africa was home to substantial populations of Homo sapiens during the late Pleistocene. Archaeological sites from this region document continuous human occupation spanning tens of thousands of years. If the core population of the species was in a region that did not experience severe environmental disruption, then the global population would not have been pushed to near extinction. The Lake Malawi data suggest that equatorial East Africa was buffered from the worst effects of the volcanic winter. The mechanisms for this buffering are not entirely clear. One possibility is that the aerosol cloud was less dense over equatorial regions, allowing more sunlight to penetrate. Another possibility is that the region's proximity to large lakes in the Indian Ocean provided a moderating influence on temperature and moisture availability. A third possibility is that atmospheric circulation patterns continued to deliver moisture to the region even when monsoons elsewhere were disrupted. Whatever the mechanism, the result is clear. The environment around Lake Malawi remained viable during and after the Toba eruption. Plants continued to grow. Fires occurred at normal frequencies. The lake maintained its water level. This environmental stability would have supported animal populations, providing food for human hunter-gatherers. The Lake Malawi cores are not the only African climate records that show stability during the Toba period. Cores from Lake Tanganyika, another large Rift Valley lake, show similar patterns. Coastal sites in South Africa also show evidence of continuous human occupation. Collectively, these records paint a picture of regional variability. The Toba eruption had severe effects in some regions, but Africa, particularly equatorial Africa, was relatively insulated. This interpretation does not diminish the power of the eruption. The climatic effects were real and significant. But they were not uniformly catastrophic across the globe. The regional variability in climate response meant that some human populations faced extreme challenges, while others persisted in relatively stable environments. The survival of the species did not require humanity to endure a global near extinction. It required adaptation in stressed regions and continuity in stable ones. The archaeological record provides a direct window into human responses to environmental change. Stone tools, hearths, animal bones, and other artifacts preserve evidence of human activities. When populations face severe stress, this evidence should reflect it. Sites should be abandoned. Tool diversity should decline. The density of artifacts should decrease. If the Toba eruption pushed humanity to the brink of extinction, the archaeological record should bear witness. In India, one of the regions closest to the eruption, several archaeological sites preserve evidence spanning the Toba event. The Jwalapuram site in the Jureru River Valley of southern India is among the most important. The site contains sedimentary deposits that include a layer of Toba ash. Stone tools are found both below and above this ash layer. The tools belong to the Middle Paleolithic tradition. They are made by striking flakes from cores of stone, then further shaping the flakes into specific forms. The technology is sophisticated, requiring knowledge of stone properties and practiced hand-eye coordination. The tools include scrapers, points and blades, each suited to particular tasks: butchering animals, working wood, or processing plant materials. When researchers examined the stone tools from Jwalapuram, they found continuity across the ash layer. The tools below the ash are Middle Paleolithic. The tools above the ash are also Middle Paleolithic. The methods of manufacture are the same. The raw materials are the same, sourced from local quartzite deposits. The types of tools produced are similar. This continuity indicates that the same population, or populations using the same technology, occupied the area before and after the eruption. The presence of tools above the ash layer is significant. It means that humans returned to the site after the ashfall. They did not abandon the region permanently. They adapted to the altered landscape and continued their activities. The ash layer itself is several centimeters thick at Jwalapuram, indicating substantial deposition. The immediate aftermath of the eruption would have been devastating locally. Ash would have buried vegetation, contaminated water, and made the environment difficult to navigate. Yet humans persisted or returned once conditions improved. The Toba site in northern India tells a similar story. Located in the Middle Sun River Valley, Toba contains sediments spanning approximately 80,000 years. The Toba ash layer is present in these sediments. Stone tools are found throughout the sequence, including layers immediately before and after the ash. The tools at Toba are also Middle Paleolithic in character. They show continuity in manufacturing techniques and tool types. There is no evidence of a technological disruption corresponding to the Toba eruption. The population maintained its cultural practices through the event. These findings from India are important because they come from sites relatively close to the eruption source. If any region should show evidence of catastrophic population collapse, it would be India. The ashfall was thick. The environmental disruption would have been immediate and severe. Yet the archaeological evidence indicates persistence and continuity. This does not mean that the eruption had no impact. The ashfall would have caused short-term abandonment of some sites. Populations may have moved to areas with less ash deposition or to locations with more reliable water sources. The density of artifacts at some sites does appear to decrease around the time of the eruption, suggesting reduced population density or changes in settlement patterns. But these changes are not total or permanent. Humans adapted to the new conditions and continued to occupy the region. Evidence from other regions supports this interpretation. At Pinnacle Point in South Africa, the site where Toba ash was first identified in Africa, the archaeological sequence shows continuous human occupation. The tools found in layers containing the ash are similar to those in layers above and below. The inhabitants of Pinnacle Point continued to exploit marine resources, collecting shellfish from the rocky coastline. The site was not abandoned during or after the Toba event. In the Levant, the region encompassing modern-day Israel, Lebanon and Syria, archaeological sites from the late Pleistocene show evidence of Neanderthal occupation. Neanderthals were a separate species of hominin, closely related to Homo sapiens but distinct. If the Toba eruption had caused a global catastrophic climate event, Neanderthal populations should have been affected as well. Studies of Neanderthal population genetics and archaeological sites do not show evidence of a dramatic population crash at 74,000 years ago. Neanderthal populations fluctuated over time, responding to glacial interglacial cycles and other environmental changes. But there is no clear signal of a Toba-related collapse. Neanderthals persisted in Europe and the Near East for tens of thousands of years after the eruption, eventually going extinct around 40,000 years ago for reasons unrelated to Toba. The archaeological evidence from multiple regions and multiple species of hominins points to the same conclusion. The Toba eruption caused regional disruption. Some areas were more severely affected than others, but there is no evidence for a universal catastrophic population collapse. Humans and other hominins adapted to the changed conditions and persisted. The continuity observed in stone tool technologies is particularly telling. Technology is transmitted culturally. passed from one generation to the next through teaching and observation. If a population is reduced to a tiny remnant, cultural knowledge can be lost. Complex technologies may be simplified or abandoned. The fact that Middle Paleolithic technologies continued unchanged through the Toba event suggests that populations remained large enough and cohesive enough to maintain their cultural traditions. This does not mean that individuals did not suffer. The volcanic winter would have brought hardship. Colder temperatures, reduced food availability, disrupted water sources. Some groups undoubtedly perished. Local extinctions occurred. But the species as a whole and the cultural knowledge it carried survived. The ash settled, the aerosols dispersed, and humans continued. Among the various environments available to early humans, coastlines held unique advantages. The boundary between land and sea is a place of concentrated resources. Tides create intertidal zones where marine organisms are exposed and accessible. Rocky shores host shellfish that can be gathered without specialized tools. Estuaries, where rivers meet the ocean, are among the most productive ecosystems on Earth, supporting dense populations of fish, birds, and invertebrates. During the late Pleistocene, sea levels fluctuated with the advance and retreat of ice sheets. When ice sheets grew, water was locked up in glaciers, and sea levels dropped. Coastal shelves that are now underwater were exposed as dry land, extending the coastline seaward. When ice sheets melted, sea levels rose, drowning coastal areas. These fluctuations meant that ancient coastlines are often now submerged, making archaeological investigation difficult. Pinnacle Point, on the south coast of South Africa, is an exception. The site is located on a rocky headland that has remained above water even during periods of high sea level. The caves and rock shelters at Pinnacle Point have been occupied intermittently by humans for hundreds of thousands of years. The sediments within these shelters preserve a detailed record of human activities. Research at Pinnacle Point has revealed that humans were exploiting marine resources there as far back as 160,000 years ago. The evidence includes the shells of marine mollusks, particularly brown mussels and turban snails, which were collected from the intertidal zone. The shells show signs of having been roasted, a method of cooking that makes the meat easier to extract. Charcoal from hearths indicates that fires were used regularly. The exploitation of marine resources at Pinnacle Point intensified during periods of environmental stress. During cold glacial periods, when terrestrial ecosystems were less productive, the inhabitants of Pinnacle Point relied more heavily on shellfish. The marine environment provided a stable, predictable food source that was less affected by changes in temperature and rainfall on land. The discovery of Toba ash at Pinnacle Point allowed researchers to examine human activities during the volcanic winter. The ash layer is found within sediments that also contain stone tools, shellfish remains, and other evidence of human occupation. Importantly, the occupation does not stop at the ash layer, it continues above it. Humans were present at Pinnacle Point before, during, and after the Toba eruption. The shellfish assemblages show no significant change around the time of the eruption. The types of species collected remain consistent. The size distribution of shells is similar. This suggests that the marine ecosystem along the south coast of South Africa was not severely disrupted by the volcanic winter. The ocean, with its large thermal mass, would have buffered against rapid temperature changes. Upwelling currents along the coast, which bring nutrient-rich water from the deep, would have continued to support productivity. For the humans at Pinnacle Point, the coastline was a refuge. While terrestrial ecosystems may have been stressed by cooling, dimming, and reduced rainfall, the marine environment remained productive. Shellfish could be gathered during low tide, providing a reliable source of protein and essential nutrients, including omega-3 fatty acids important for brain function. The predictability of tidal cycles meant that food was available on a regular schedule, regardless of seasonal variations on land. The stone tool assemblages from Pinnacle Point during the Toba period include small, carefully made blades. These tools are typical of the Still Bay tradition, a distinctive Middle Stone Age technology found in southern Africa. The Still Bay tradition includes bifacial points, thin and symmetrical tools that were probably used as spear tips or knives. The production of these tools requires considerable skill. The persistence of this sophisticated technology through the Toba period indicates that the population at Pinnacle Point remained stable and capable of maintaining complex cultural practices. Coastlines elsewhere in Africa likely served similar functions as refugia. The Mediterranean coast of North Africa, the Red Sea coast, and the East African coast all would have provided access to marine resources. Unfortunately, many ancient coastal sites are now submerged due to sea level rise, making it difficult to recover archaeological evidence. The sites that do exist, like Pinnacle Point, provide a glimpse of a broader pattern. The reliance on coastal resources may have been a critical adaptation that allowed some human populations to survive the Toba volcanic winter. Terrestrial ecosystems, dependent on photosynthesis and disrupted by dimming and cooling, would have suffered productivity losses. Marine ecosystems, particularly in coastal zones, would have been more resilient. The ocean's thermal inertia would have moderated temperature changes. Nutrient cycling in the ocean would have continued, supporting primary productivity by phytoplankton, which in turn supported fish and invertebrates. This resilience made coastlines attractive to human populations during periods of environmental stress. Groups that had knowledge of marine resources, that knew how to gather shellfish and catch fish, would have had a significant survival advantage. This knowledge was not universal. It required learning and cultural transmission. Populations that lacked this knowledge, or that lived far from coastlines, would have been more vulnerable to the disruption of terrestrial food sources. The coastline strategy was not just about food. Coastal areas often have freshwater springs where groundwater emerges near the shore. These springs would have provided reliable drinking water, even during droughts that affected rivers and lakes inland. The combination of food and water made coastlines ideal refugia during the volcanic winter. The archaeological evidence from Pinnacle Point demonstrates that at least some human populations successfully navigated the Toba event by relying on coastal resources. The continuity of occupation, the persistence of sophisticated tool technologies, and the stable exploitation of marine resources all point to a population that was not on the brink of extinction, but adapting effectively to environmental challenges. The coastline was not merely a place of survival. It was a place where culture and knowledge endured. Inland, away from the moderating influence of the ocean, the challenges posed by the Toba volcanic winter would have been more severe. Cooling, dimming, and disrupted rainfall would have stressed terrestrial ecosystems. Yet even in these environments, certain features of the landscape provided refugia. Rivers were among the most important. Rivers create linear corridors of productivity through landscapes that may otherwise be arid or unproductive. They provide water, which is essential for all life. They support riparian vegetation, which provides food and shelter for animals. They concentrate fish and other aquatic resources. During droughts, when the surrounding landscape dries out, rivers become focal points where life persists. The Shinfa Matema site in northwestern Ethiopia provides evidence for how humans exploited riverine resources during the Toba period. The site is located along a tributary of the Blue Nile River in the lowlands of the Ethiopian plateau. Today, the region experiences strong seasonal aridity. The rainy season brings abundant rainfall, swelling the rivers. The dry season is harsh, with little rain and high temperatures. Analysis of fossil mammal teeth and ostrich eggshells from the site reveals that this seasonal pattern existed 74,000 years ago as well. Isotope geochemistry, which examines the ratio of stable isotopes in biological tissues, provides information about the climate and environment in which an organism lived. Oxygen isotopes reflect the source of drinking water and the evaporation rate, which varies with temperature and humidity. Carbon isotopes reflect the types of plants consumed, which in turn reflect rainfall and vegetation patterns. The isotope data from Shinfa Matema indicate that the region experienced pronounced seasonal aridity. During the dry season, water sources would have been limited. Rivers would have slowed or stopped flowing in their upper reaches, leaving only isolated pools in the deeper sections of the river channel. These pools, sustained by groundwater seepage or by water stored in upstream reservoirs, became critical resources. The presence of Toba ash at the site confirms that humans were living there during and after the eruption. The ash layer is found within sediments that also contain stone tools, animal bones, and other evidence of human activity. The stone tools belong to the Middle Stone Age, the African equivalent of the Middle Paleolithic. They include small, symmetrical triangular points that are among the oldest known evidence of projectile technology, possibly arrows. The animal bones at the site include remains of fish and terrestrial mammals. The fish bones indicate that humans were harvesting aquatic resources from the river. The terrestrial mammal bones include species that are adapted to arid environments, such as certain antelopes. The presence of these bones suggests that humans were hunting animals that came to the river to drink. During the dry season, the shrinking waterholes would have concentrated prey. Animals that required regular access to water would have been forced to visit these remaining pools. This created a predictable situation for human hunters. By positioning themselves near waterholes, hunters could intercept animals with high efficiency. The invention of projectile technology, such as the bow and arrow, would have made this hunting strategy even more effective, allowing hunters to kill prey from a distance without putting themselves at risk. The riverine adaptation at Shinfa Matema represents a sophisticated response to environmental stress. The humans at the site were not passively enduring the volcanic winter. They were actively exploiting features of the landscape that provided concentrated resources. The seasonal rivers, or blue highways as they have been called, acted as ecological attractors, drawing both animals and humans. This adaptation would have been particularly effective during the Toba volcanic winter, when the disruption of monsoons and the reduction in rainfall would have made many areas more arid. The rivers, fed by highland sources or by persistent groundwater, would have continued to flow even when local rainfall failed. The pools left behind during the dry season would have been oases in an otherwise inhospitable landscape. The projectile technology found at Shinfa Matema is significant. Arrows represent a technological advancement over hand-thrown spears or thrusting spears. Arrows can be launched from a greater distance, increasing hunting success and reducing risk to the hunter. The small symmetrical points found at the site are consistent with arrow tips. Their presence at 74,000 years ago, during the Toba period, suggests that environmental stress may have driven technological innovation. Groups that developed more efficient hunting technologies would have had higher caloric returns from scarce prey, improving their chances of survival. The riverine strategy was not unique to Shinfa Matema. Other sites along rivers in Africa and elsewhere likely employed similar approaches. Rivers like the Nile, the Niger, the Zambezi, and the Congo would have served as lifelines during the volcanic winter, supporting human populations when the surrounding landscape was stressed. The importance of rivers extends beyond food and water. Rivers also serve as corridors for movement. During periods when the landscape between river systems became arid and difficult to traverse, rivers would have provided routes for migration and communication between groups. Following a river downstream leads eventually to the ocean or to a lake. Following it upstream leads to highlands or to tributaries connecting to other watersheds. This connectivity would have been important for maintaining social networks and for allowing populations to move in response to changing conditions. The evidence from Shinfa Matema demonstrates that even in regions that experienced increased aridity during the Toba volcanic winter, humans were able to adapt and persist by exploiting riverine resources. The combination of reliable water, concentrated prey, and aquatic foods provided a stable subsistence base. The development of advanced hunting technologies enhanced efficiency. The result was not extinction, but adaptation. The rivers were lifelines, sustaining human populations through the darkest years of the volcanic winter. Technology is a defining characteristic of humanity. The ability to create tools, to modify the environment, and to develop new techniques sets humans apart from most other species. During the late Pleistocene, human technology was already sophisticated. Stone tools were shaped with precision. Fire was controlled and used for cooking, warmth, and protection. But the Toba period may have witnessed an important technological innovation, the development of projectile weapons. Projectile weapons allow a hunter to kill prey from a distance. This offers several advantages. It reduces the physical risk to the hunter, who does not need to engage in close combat with dangerous animals. It allows the hunter to target prey that is wary or fast-moving, which might be difficult to approach closely. It increases the effective range of hunting, allowing access to resources that would otherwise be unavailable. The earliest projectile weapons were likely throwing spears, which are hurled by hand. Throwing spears have been used by humans for hundreds of thousands of years, but throwing spears have limitations. The distance they can be thrown accurately is limited by human arm strength and coordination. The impact energy decreases with distance. They are most effective at ranges of 10 to 20 meters, The development of the atlatl, or spear thrower, extended the range and power of thrown spears. An atlatl is a lever that increases the velocity of the spear by extending the length of the throwing arm. Atlatls have been used by many human societies and are first documented archaeologically around 30,000 years ago, though they may have been invented earlier. The bow and arrow represents a further advancement. A bow stores energy in the flexed limbs and releases it rapidly when the string is released, propelling the arrow at high velocity. Arrows are smaller and lighter than spears, allowing a hunter to carry many arrows and take multiple shots. Bows are effective at ranges of 30 to 50 meters or more, depending on the design. The invention of the bow and arrow is difficult to date precisely because the materials involved, wood and plant fibers, do not preserve well in the archaeological record. What does preserve are the stone points that tip the arrows. These points are small, light and symmetrical, designed to fly straight and penetrate effectively. They are distinct from the larger, heavier points used on spears. At the Shinfa Matema site in Ethiopia, researchers found small, symmetrical triangular stone points in sediments dating to approximately 74,000 years ago, the time of the Toba eruption. These points are consistent with arrow tips. They are small, typically less than 3 centimeters in length. They are thin and carefully shaped with sharp edges and pointed tips. The workmanship is precise, indicating skilled manufacture. The identification of these points as arrow tips is based on comparative analysis with points from later periods that are definitively associated with bows and arrows, as well as experimental studies that test how different point designs perform when launched from bows versus thrown by hand or with an atlatl. The small size and light weight of the Shinfa Matema points are most consistent with use as arrow tips. If this interpretation is correct, it means that humans at Shinfa Matema had developed archery by 74,000 years ago. This would make these points the oldest known evidence of bow and arrow technology, predating other candidates by tens of thousands of years. The context in which these points were found is significant. Shinfa Matema is located in a region that experienced increased aridity during the late Pleistocene. The disruption of monsoon patterns by the Toba eruption would have exacerbated this aridity. Prey animals would have been scarce and wary. Hunting success would have been critical for survival. The development of archery under these conditions makes adaptive sense. Bows and arrows increase hunting efficiency. They allow hunters to take shots at greater distances, reducing the chance that prey will detect the hunter and flee. They allow hunters to target specific individuals within a herd, such as juveniles or females, which may be more vulnerable. They reduce the physical exertion required for hunting, as the bow does the work of accelerating the projectile. The technological innovation represented by the bow and arrow may have been driven by necessity. Groups facing severe resource scarcity needed to maximize their caloric return from hunting. Those that developed more effective hunting technologies would have had a survival advantage. The invention of the bow and arrow at Shinfa Matema during the Toba period suggests that environmental stress acted as a driver of innovation. This pattern, where stress drives innovation, is seen repeatedly in human history. When conditions are stable and resources are abundant, there is less pressure to develop new technologies. When conditions deteriorate and resources become scarce, innovation becomes advantageous. Groups that can adapt technologically are more likely to survive. The bow and arrow is not the only technological innovation that may have emerged during the late Pleistocene. Other examples include the development of hafting techniques to attach stone points to wooden shafts, the use of composite tools made from multiple materials, and the creation of specialized tools for processing plant foods. Each of these innovations reflects the same underlying capability, the ability to identify problems and develop solutions. The cognitive abilities required for technological innovation are considerable. Toolmaking requires an understanding of material properties, spatial reasoning, and fine motor control. Innovation requires the ability to imagine something that does not yet exist, to experiment with new approaches, and to learn from failures. These cognitive abilities are characteristic of modern Homo sapiens and are part of what allowed our species to adapt to diverse and changing environments. The stone points from Shinfa Matema are small objects easily overlooked, but they represent something profound. They are evidence of human ingenuity in the face of adversity. During a period of global environmental stress, when food was scarce and survival uncertain, humans did not simply endure. They innovated. They developed new technologies that increased their effectiveness as hunters. These innovations, passed from one generation to the next, became part of the cumulative cultural knowledge that defines humanity. The bow and arrow, first invented perhaps 74,000 years ago, during the darkest years of the Toba volcanic winter, remains in use today, a testament to the enduring power of human creativity. Among all the adaptations that allowed Homo sapiens to survive the Toba volcanic winter, one stands out as perhaps most critical: social organization. Humans are fundamentally social creatures. We live in groups, cooperate in tasks, share resources, and transmit knowledge across generations. The structure of these social relationships, the size and connectivity of social networks, can determine whether a group survives or perishes during times of environmental stress. The late Pleistocene was a time when multiple species of hominins coexisted. Homo sapiens shared the planet with Neanderthals in Europe and Western Asia, with Denisovans in Eastern Asia, and possibly with other archaic human species in Africa and Southeast Asia. These species were similar in many ways. They all made stone tools, they all used fire, they all hunted and gathered food, yet by 40,000 years ago, only Homo sapiens remained. The others had gone extinct. The reasons for these extinctions are complex and debated. Climate change, competition for resources, and interbreeding all played roles. But one factor that may have given Homo sapiens an advantage was the structure of their social networks. Archaeological and anthropological evidence suggests that Homo sapiens formed wide-ranging cooperative social networks that extended across large territories. These networks connected multiple residential groups, or bands, that lived in different locations but maintained social ties through kinship, ritual, and exchange. When one group faced resource shortages, it could call on other groups for assistance. When new information or technologies were developed, they could spread rapidly through the network. This type of social organization has been called a tribal model. Tribes are not centralized political entities, but rather networks of related groups that recognize common identity and maintain relationships through periodic gatherings, intermarriage, and shared rituals. Modern hunter-gatherer societies provide examples of this type of organization. Studies of groups like the Kung San of southern Africa or the Aboriginal Australians document extensive social networks that span hundreds of kilometers. Individuals maintain relationships with relatives and allies in distant bands, and they can travel to these groups during times of resource scarcity. The benefits of such networks during environmental stress are substantial. If a drought affects one region, groups in that region can move to areas where conditions are better, relying on their social ties to gain access to resources. If a technological innovation is developed in one group, it can spread to other groups through social learning. If a local group suffers high mortality from disease or accident, it can be replenished by individuals from other groups, preventing local extinction. In contrast, other hominin species may have operated with more restrictive social structures. Neanderthals, based on archaeological evidence, appear to have lived in smaller, more isolated groups. The territories they occupied were smaller. The exchange of materials and ideas between groups appears to have been limited. Some researchers have described this pattern as more similar to chimpanzee troop organization, where groups maintain exclusive territories and interaction between groups is minimal or hostile. This difference in social organization would have had consequences during the Toba volcanic winter. For Neanderthals, a group facing resource scarcity in its territory would have had limited options. If local resources were exhausted, the group might attempt to move into neighboring territories, potentially leading to conflict. If the group remained in place, it risked starvation. The lack of extensive social networks meant there was no buffer against local failures. For Homo sapiens, the situation was different. A group facing scarcity could draw on its social network. It could move to the territory of an allied group, where resources might still be available. It could receive food or information from distant relatives. The network provided resilience, distributing risk across a larger population. This resilience would have been critical during the decade-long volcanic winter following the Toba eruption. The disruption was not uniform. Some regions were more severely affected than others. Some groups would have faced catastrophic resource failures. Others would have had access to refugia with more stable conditions. The social networks of Homo sapiens would have allowed information about these refugia to spread. Groups in severely affected areas could learn where conditions were better and attempt to move there. The maintenance of such networks required specific cultural practices. Rituals and ceremonies served to reinforce social bonds and mark group identity. Exchange of objects, such as shells, ochre, or stone tools made from exotic materials, served as tangible symbols of relationships and obligations. Language, with its capacity for abstract communication, allowed for the transmission of complex information about resources, routes, and social relationships. These cultural practices are visible in the archaeological record of Homo sapiens during the late Pleistocene. Sites contain evidence of long-distance exchange, with materials sourced from locations hundreds of kilometers away. Burials include grave goods, suggesting belief systems and ritual practices. Symbolic objects, such as beads made from shells or engraved ochre, indicate the importance of identity and communication. Neanderthal sites from the same period show less evidence of these practices. Exchange networks appear to have been more local. Symbolic objects are rare. This does not mean Neanderthals lacked culture or intelligence, but it suggests that their social organization was structured differently, with less emphasis on long-distance relationships. The consequences of these different social structures became apparent during times of environmental stress. Neanderthal populations declined significantly during the cold periods of the late Pleistocene. By 40,000 years ago, they had gone extinct. Homo sapiens, meanwhile, not only survived but expanded, eventually colonizing every habitable continent. The Toba volcanic winter may have been one of many stresses that tested these different social strategies. Groups that operated in isolation, with limited social networks, were vulnerable to local resource failures. Groups that maintained extensive social networks had buffers and alternatives. Over time, the cumulative effect of many such stresses would have favored the more resilient social structure. The network that endured was not just a collection of individuals, it was a web of relationships, maintained through effort and cultural practice. It was a system for sharing information, resources, and support. It was, in a sense, a technology as important as the bow and arrow or the control of fire. It was a social technology, a way of organizing human cooperation that increased the survival chances of the group. During the darkest years of the volcanic winter, when ash dimmed the sky and cooling stressed the land, it was this network that held. Small groups, scattered across Africa and beyond, maintained their connections. They shared knowledge of refugia, of coastal resources, of riverine lifelines. They supported each other through the hardship. And when the aerosols finally settled and the sun's light returned to full strength, it was these connected groups, these cooperating bands, that emerged into the recovering world. The species had survived, not through individual heroism, but through collective resilience. The network that endured became the foundation for all that followed.